Hello and welcome back. This is a module on some of the features made available with System Verilog forDesign. System Verilog was introduced in the 2000s as a follow-on to Verilog 2001. Many features support verification, which is not the subject of this class, but there are a number of features that support design that made designs more readable and more compact. And I'm going to go through some of those major features here. This information is largely taken from the textbook, Sutherland. I'm just going to get a pointer going here. Sutherland, Daveman and Flake, System Verilog forDesign. So there's a whole book on this subject, so I'm just covering what I think are some of the more important features. While I'm doing this, many industry groups are starting to use System Verilog for new designs and using these features. There's also essential source of common interview questions that I've seen. What I'm going to go through is mainly different data types and collections of data types that are useful to designers to varying degrees. This is logic and bit, arrays. Specifying logical intent is not a data type, but it has some utility, and I'll explain why. And I'll explain its limitations as well. I'll go through different data types: enum, struct, typedef to declare different data type, and union. Package collects these things together in one place, and interface can be used to specify buses communicated through module headers. Now you're familiar with reg and wire in the context of Verilog 2001, and you're by now very familiar with the fact that reg does not mean it's a register, and this can be confusing. So taking the relatively simple fix in Verilog 2001 of also providing logic and bit. Logic can take on values 0, 1, x, and z, and so it replaces reg and wire quite directly. Bit, however, can only take on the values of 0 and 1. I'd argue that the value of propagating don't cares in the start of a simulation, so you know that reset was handled correctly, is useful, and thus you use like type logic. This simply prevents syntax errors when you misdeclare something should be of type reg as type wire, or vice versa. Arrays have improved substantially in Verilog, System Verilog. In Verilog 2001, you only have one array type, and that is a 1D array of vectors. So in the register file we saw we had 32 16-bit vectors. And you could refer to one of those vectors in an assignment, and that's the only allowed assignment. System Verilog has liberalized this to a very large degree. We have packed arrays. Here, for example, we have a 32-bit vector broken into 4 8-bit subfields, and referring to those individually can be quite useful, and we'll see an example of this in a few minutes. And thus you can refer to subfields individually, and you can also refer to individual bits. That is useful as well. Multi-dimensional arrays are new to System Verilog over Verilog 2001. In contrast, in Verilog 2001, we only have a one-dimensional array of bytes, one-dimensional arrays of vectors. Here, for example, a one-dimensional array of bytes. In System Verilog, we can have multi-dimensional arrays. For example, RGB is 3 dimensions, a 3-dimensional array of bytes. And you can again pull out one particular byte of both of these through appropriate references. This can be quite useful, and particularly as there's a lot of variables that are expressible as multi-dimensional arrays. But be careful, if you build these as registers, they can end up being very, very large. Number of useful features: arrays can be assigned to each other at long last. So for example, here we have a 16 element array and a 256 element array, and we can assign part of the big array to the small array in one single line of assignment. We can also assign numbers in arrays, variables in arrays, using curly brackets. With this dash curly brackets nomenclature can be used to default all the array elements as 0 or to a particular number. So we can reset all elements of the array in one statement in System Verilog. Or we can assign a load the array with a particular value, mixed combination of numbers and variables using this dash curly bracket. We can pass arrays via module ports. To do this, I have to introduce you to typedef, which is exactly that, defining a data type, a new data type. So here we define a new data type as being a two-dimensional array of 32-bit numbers. Note that the data type has _t associated with it, indicating it's a data type, not a data. Now we can use that in our module headers to pass multi-dimensional arrays via the module ports. So for example, we can pass d in and q out by declaring them to be of this multi-dimensional array type in the headers for a module. And thus we can pass large multi-dimensional arrays to and from modules. Again, just be aware if you're doing this that you're defining a lot of wires potentially. Moving on, you can specify logical intent in Verilog, in System Verilog. And this is with always _ff for flip-flop, always _com for combinational, always _latch for latches. Now you might think, wow, this is useful. I can prevent all those subtle bugs where I accidentally have unintentional latches and so on and so forth. Well, unfortunately, it doesn't do that. It does not relieve you of coding it correctly. All it does is give you an extra warning if you do code it incorrectly. So it's not a panacea, but it is useful for those extra warnings. A very useful feature in System Verilog is enum for enumerated data types. So for example, we can specify the we have here a state vector. We're declaring state and next state. Instead of using parameter, which we'll see in a moment, we're using enum for this data type. And we're assigning the symbolic names wait, load, and done to numbers using the enum data type. Before, in Verilog 2001, we used parameter to do this. A parameter to substitute the symbolics wait, load, and done with numbers. In this case, in both examples, they're one hot and coded. But here in this example, we've intentionally introduced a bug. Done has the same encoding as wait. And unfortunately, in Verilog 2001, that's perfectly legal. And thus, there's a bug here, but the bug is not discovered until we're simulating it and seeing errors in our states. And this one can be a tough one to track down because it's in the parameter declaration. So this is whereas in contrast with enum, if you did this, if you assign done to be 001 as well, that's a syntax error now, and it will be flagged as such an error early in the design process. So this is a very useful feature when you want to enumerate state encodings in a finite state machine in a bug-free fashion. There's also a struct data type which allows better organized, more readable data. This mainly improves readability. So for example, we could declare this as a one-dimensional vector simply of 132 bits or logics. And just carry in our head that the first 32 bits are the source address, the next 32 bits the destination address, and so on. Well, that's perfectly legal, and that's what we'd have to do in Verilog 2001. But in System Verilog, we can explicitly have these subfields in the structure element. So we can declare a structure where this array of bits are broken down into the actual functions of these sub-elements. And we can address these sub-elements individually with this dot structure, syntax. So packet.source address can be assigned a number or another variable. So this makes the code much more readable because you can specify the sub-elements in the addresses. You can also assign the struct using the curly brackets, dash curly brackets, with the 4 fields assigned here. And again, you can pass this structs by module ports by declaring a typedef for the struct. Again, _t is a typedef, and declaring the module port headers. We use that typedef and refer to the actual variable inside the module just like you do here. So this is a useful feature for aiding readability of code to break down a long vector into a series of functional short vectors. Union is also introduced with system Verilog, and again it's much like C. Only a packed union is synthesizable. The basic idea is that the union can have 2 different representations or multiple different representations depending on what you're doing. So in this example, we have instructions in an instruction set architecture, and some of those instructions contain opcodes. Some of those instructions are just data that's appended onto the instruction with the opcode. And what union packed allows you to do is to use the appropriate data type when you know that it's an opcode type instruction, or know that it's just an extension with the data. And so here, for example, union packed is the data type. We have one version, that's the struct up here, data type _t for the data type packet. And we have our packed array that we saw earlier of 8 8-bit bytes packed together into one 32-bit word. And we can refer to these by dereg packet and dereg bytes. And again, this increases the readability of the code when the human realizes this is an appropriate representation. Only packed union is synthesizable. So we've seen typedef quite a bit by now, and you might think, well, this is a useful feature, I'm going to start using typedef. And you start writing this into your code, and you discover that you've lost track of where these types are. So System Verilog also introduces this package concept to allow you to collect together all the types and functions and tasks associated with a particular part of the design. So here we have a package called ALU types, and we have different type defs specified here, including structs, and we can collect them all together in one place. Makes the code easier to maintain by knowing where these declarations are. And of course, if we make a declaration like this, we need to be able to refer to it in the modules we're building, and there's multiple different ways of doing that. There's the explicit method where we have to spell out the package name. Remember, ALU types was the package name. Have this double colon to refer to a specific data type declaration within that package. And this is the most explicit way of specifying this element of the package. Or we can, if we know we're going to do this again and again, we can import that particular data type. So here we have import ALU types bus64 _t. So now we've imported bus64 _t, and we can use bus64 _t without the ALU types double colon prefix. Finally, we can do wildcard imports that import all the definitions within the package. For example, ALU types is the package name, : star imports all the definitions. Now can refer to them without ALU types. This is most useful if we know we're going to be using many of the different types within a particular package. Finally, we're going to deal with interface. You've already started to see that module headers can get quite large in Verilog 2001, and you have to maintain those. Whenever you add a variable to a module header, you have to name it. In a shared bus type situation, you have to do it in all the connected modules. So for example, here we have a master processor, a slave processor, an internal memory, all communicating on a bus. And each of these has a module header related to this interface. And we have to maintain that module header. Whenever we add a bit, we have to add it to all the interface, all of the module headers of all three modules. This can get rather tedious and is bugged and prone to be buggy and makes the code harder to read. And System Verilog introduced the interface data structure to make this easier to deal with. So here's an example. On the left, we have two processors connected by a bus, and we have to type out all of these ports and type them correctly and connect them to internal variables inside the modules. And again, that can be rather tedious and error prone. Instead, in System Verilog, we specify a module interface or a set of connections in one structure called a interface. And here we just declared all those data types, all those variables that we have on the previous page. Notice a couple are declared as type wire. This is because they're tri-statable and multi-directional. And now all we have to do is refer to main bus in our module headers to specify an interface that is of this collection of connections. And we can do that in our top level module. We can do that in our subordinate modules where we're actually connecting them together. So .bus connects them to the bus type within the module. Now you might think, well, sometimes you might need small changes, for example, to change the direction of a signal. And that is anticipated in System Verilog with modport. Modport allows interfaces to be customized for different module types within a set of connected module types. So for example, here we have a master and a slave modport. And what changes here is the directions of things like the address. But there's still one interface type and thus can be referred to collectively. We might have a primary that's a master, and so this is a bus.master, and we might have a secondary slave, bus.slave, and thus we can refer to the right modified port list as appropriate for the function of the module that we're connecting to it. Well, that brings us to the end of this section. What I've done is introduce you to some of the major features of System Verilog that have utility. Most of the time, this utility is to save typing and improve designer productivity, or to make code more readable, or in the case of multi-dimensional arrays, make the code more compact and easier to code. And in the type of packages and typedef, convenience factors to collect them together to again improve designer productivity, and as interfaces does as well. I consider the most useful features here for the sort of scale of designs we're doing in this class to be logic and bit, particularly logic. You notice logic is used quite a bit, just to save, well, is this type wire, is this type reg, what are the rules again? And enum. Enum is very useful in preventing bugs creeping into finite state machine specifications. I haven't covered all the features in synthesizable System Verilog. There's a lot of other features, for example, plus equal and plus plus from C, which can be useful to designers as well, though a relatively minor utility. I hope you've enjoyed this section. Thank you very much for your attention.